In this segment, we are going to talk about the impact testing. Based off the requirement of the ASME Code Section 8, we need to assess any pressure vessel that we are designing to see if it needs to be impact tested or is going to be exempted from the impact testing. So if I'm having this plate, which is a SA516 grade 70, if I drop this piece of the plate from 6 feet on a concrete floor, I hear a noise, but nothing can happen for this if I drop this. But if I submerge this carbon steel material SA516 grade 70 to the liquid nitrogen, and then you know the liquid nitrogen, almost the temperature is minus 347 degree Fahrenheit, and I submerge there and stay for a few minutes to get stabilized, and the temperature of this material turns to the minus 300 degree Fahrenheit or even less, and then I take it out and I drop this on a concrete floor or hit it a little bit to the concrete floor. This might be break. I have no doubt it's going to break in several pieces. So it's going to break. If you look at the area that the failure happened and to the surface of the point that it's broken, we're going to see a very sharp edges, like the way the glasses breaks. So this is a thing that is not desired for design purposes. We need the material have a good resistance about the impact and the lower temperature. I said minus 300 degree Fahrenheit, but for our imaginary pressure vessel, now the temperature is minimum design metal temperature is minus 30 degree Fahrenheit. So we need to analyze, we need to assess to see if our pressure vessel is going to be impact tested or is going to be exempted from impact testing. So impact testing is what we are doing in here to see if our material has enough toughness about the impact or any shock in lower temperature, which is for our case is minus 30 degree Fahrenheit in here. And you know the material transfers from the ductile phase to the brittle phase in a certain temperature. So it's different from any material. So for some material, they are transferred from the ductile phase to the brittle phase at minus 10 degree Fahrenheit. For some of them, with a different alloy, they might transfer at the minus 60 degree Fahrenheit. They have a more toughness regarding the impact. So it depends on the alloy material we are using. Also, the thickness is playing an important role in here. For example, for this material SA516 grade 70, you can use this material up to minus 30 degree Fahrenheit when the thickness is 1 inch. But if you go to the 3.25 inch, which is our nominal thickness, we can use this material safely on the, up to 14 degree Fahrenheit. I put in the screen, you can see. So this material can operate on 14 degree Fahrenheit without doing any impact testing. It means at the 14 degree Fahrenheit with the 3.25 inch is safe to work, and it's not going to be any susceptibility to the brittle fracture at this temperature with this thickness. But if you go to the 1 inch a lower thickness, we can use this material up to minus 30 degree Fahrenheit. So there's a different factors in here. We don't want to open the metallurgy in here, but what we want the subject of the metallurgy in here, but what we want trying to say in here is that the material transfers from the the ductile phase to the brittle phase in a certain temperature, and it's not going to be safe when it is in the brittle phase. What happened to the Titanic ship is the same story. The material is used didn't have enough toughness at that certain temperature in the sea. So when it's hit the iceberg, and instead of a deformation that we expected to create a dent in the ship body or even create a hole in one point with the deformation, like iceberg pushed the body of the ship and made a dent on that. and create a hole, but it didn't happen. It caused a crack, and the crack propagated, and a brittle fracture happened and caused the sinking of the ship. So the same things happens in here. We are having a pressure vessel in here. This might go to the industry, works for 30 years, and exists a micro crack somewhere in one of these wells. And by the chance, we couldn't catch that micro crack by the radiography testing, and it's existed and it works for 30 years and nothing happens. But if it goes to the lower temperature and a mechanical shock happens by draining the liquid and pushing the new liquids and going fluctuation or a shock or something like that, that's little micro crack might propagate, or impact on the pressure vessel. It might be propagate that micro crack and change to the catastrophic brittle fracture, like the one you can see in the screen. There's a pressure vessel, something happened, a shock or something, and caused the brittle fracture. Even this happens in the hydrostatic testing that we are going to review in upcoming segments. Sometimes the weather is so cold, and then they make the hydrostatic testing at the lower temperature, and close to the minimum design metal temperature, and sometimes that cause a brittle fracture just in the shop before leaving the pressure vessel from the manufacturing shop, and it breaks. Like the photo you can see in my right, it's happened in the manufacturing shop at the hydrostatic testing. So the brittle fracture is very dangerous because there's no notice. In a ductile fracture, you having a deformation, and then a failure happens. Here, you don't have any deformation. It directly goes to the failure with the sharp edges. So the test is done. We are going to perform in here, or we are analyzing. If we didn't get exempted, we have to perform is the 10 by 10, you can see it in the screen. It's a test specimen. I'm having some things in here, like this specimen. I'm going to run this small pieces of a video on the side. Then you can see the cross section, the area that the failure happened. And this is a ductile fracture. Actually, you can see ductile fractures that have a good toughness on this material, because this is tested at the room temperature. So I didn't expect this to be a brittle fracture, but this is the same material. It's completely separated in the impact testing, and still there's a good sign of the ductile fracture, but you can see it's the hammer hit these things and separated these things, but couldn't separate this, and you can see they are still one piece test specimen. How they do the test? I mean, there's lots of videos in the YouTube. You can go watch those videos and then come back in here, because we are not in here to explain the procedure of the impact testing. We are here to review the ASME Code Section 8 Division 1 requirements regarding the impact testing. But as a short explanation, there is a hammer, a very heavy hammer, and then there's a notch on these specimens, and then these hammers hits the back of this test specimen. Of course, this specimen already gone to the minimum design metal temperature. So if our minimum design metal temperature is minus 30 degrees Fahrenheit, this specimen should go to the liquid nitrogen or carbon dioxide and go to the minus 30 degrees Fahrenheit. So the conventional method is that there's a bath over there. They hold these things with the instrument and submerge to the nitrogen, but it might go to the way below minus 30 degrees Fahrenheit. There's a very advanced cooling machines that use the same liquid nitrogen or carbon dioxide, and the cooling process is performed, but it's under control. So when you are adjust on minus 30 degrees Fahrenheit, they're going to use a liquid concentration or the process to take this temperature to the minus 30 degrees Fahrenheit and not minus 35 degrees Fahrenheit. But the conventional method is that they are just submerged on on a liquid, and a nitrogen liquid, and then put in the machine. So if these hammers hit this test specimen from the back side, the notch is from this side and from the back side, and depends how much this, after it breaks this, the breaking is not happen on this test specimen, but when it breaks, it goes up. So if it goes too high, it indicates that this test specimen received a little energy to break these things, and this hit this, breaks this, and goes high. But sometimes it breaks this, it stopped there like the one happened for him, or breaks this, it goes a little bit high and then returns back. So this indicates to me this specimen received lots of energy from that hammer, so which is consumed those energy, and it wasn't able to go very high because it's gave those energy to the breaking of this test specimen. So there's a graduation sheet over there, and it measures. Now there's a very advanced machine, impact machine. How much this goes high, the machine measures that and calculates the foot-pound value for absorbed energy for breaking this test specimen, and then we can go and compare with the acceptance criteria. So like I said, we have to assess any pressure in any pressure vessel design process to see if our pressure vessel is going to be subjected to the impact testing, or we're going to be exempted from the impact testing. But we're going to review in here to see in what cases we're going to be subjected to the impact testing, in what temperature or thickness combination, or by the chance, if we are have to perform the impact testing, what is the acceptance criteria, how many test specimens we need to make for the impact testing. Before going to the exemption process, the ASME Section 8, Division 1 on the UG 66 divided the all carbon steel and low alloy steel material on the 4 groups. So it means you are having the 4 baskets with and you have written all the name of the UCS table 23 in a piece of the paper and put on these baskets. So you are having the basket A, basket B, basket C, and basket D. So you don't have any more material in here. All the material divided on these 4 baskets. Consider the ones with the high strength regarding the brittle fracture, or with the high toughness value goes to the basket number D. The lower than that goes to the basket number C, and the lower than that goes to the basket number B, and lower than that goes to the basket number A. So from the brittle fracture points of view, the basket A is the weakest one, and the basket D is the strongest one. So they comes with the curve. They said the curve D, curve C, curve B, curve A. You consider that curves as the groups or these baskets that I explained in here. So we are having the 4 groups or 4 curves that we're going to assess based off those curves to see if are subjected to the impact testing or we are exempted from the impact testing. And any material in the carbon steel and low alloy steel on the UCS section are assigned to the one of these curves. The process, as you can see, is in my right. First, we are going to go to the UG20F and we assess to see if our pressure vessel gets exempted from impact testing. If we are exempted, we're going to stop the assessment, and then we are going to indicate in the design documents that the impact testing is exempted for this pressure vessel with this minimum design middle temperature, with this thickness, and with this material. But by the chance, if we didn't get exempted, then you have to go to the next step, which is UCS 66A. Again, you're going to continue assessment to see if you get exempt from from the impact testing. If you get exempted by the UCS 66A, you're good to go. If not, you have to go to the next step, and the next step is the UCS 66B. You're going to assess based off the UCS 66B and to see if you can get exempted. If you exempted, stop the assessment. You don't need to proceed. But by the chance, if you couldn't get exempted by the UCS 66B, then you have to go to the next step, which is the last step, and it's the UCS 68C. If you exempted, good to go. If not, then you have to perform the impact testing on the plate material, which not be exempted. Also, you have to qualify your WPS with the impact testing. We're going to discuss those things in the ASME Section 9, but you know, based off the ASME Section 9, when you are having a welding procedure, you qualify that welding procedure with the 2 tension tests, 2 root bend tests, and 2 face bend tests. But if your pressure vessel is subjected to the impact testing, then your WPS also need to be qualified by the impact testing. It means in addition to those testing that I named them, you have to also perform 3 specimens or 1 set on heat affected zone, at the heat affected zone, and the 3 specimens, another set on the weld metal, and then qualify your WPS, and then you're going to be allowed to make a welding based off the qualified welding procedure. So this is the process. When you are subjected to the impact testing, you're going to do the impact testing on plate material or any non-exempted material that is used on the pressure vessel, and then your WPS and PQR also needs to be qualified by the impact testing. So if you already have the WPS and PQR 10 years ago or long time ago or weeks ago, whatever, and qualified with the impact testing, then you can use that WPS. But if you don't have available WPS and PQR to be qualified, a WPS to qualify with the impact test, then also you need some time and more work to qualify your WPS with the impact testing. Now, for our imaginary pressure vessel with the thickness 3.25 inch, and with the minimum design metal temperature minus 30 degrees Fahrenheit, we are going to start the assessment to see if we can get exempted from impact testing. The first process, as you can see in the screen, is UG20F. So UG20F says, you know, you have to come in here and says for P number 1, group number 1 or 2, and the thickness which is not exceeding ½ inch for material listed in curve A, and for a material which listed in the curve B, C, D, up to 1 inch exempted. So no more assessment. So if you are in the curve A and your material thickness is ½ inch, you're exempted. And if you are in the curve B, C, D, and you are on your material thickness is a 1 inch, then you are exempted. So you know the SA516 grade 70 is a P number 1, group number 2 is on curve D. It's belong to the curve D. It's classified on the curve D. But the grade 60 and 65 are on curve. So you can see the SA516 grade 70 is P number 1 and group number 2. And 60 and 61 are group number 1. So they are listed, the grade 70 is listed to the curve number D. So for curve number D, we can get exempted from the impact testing up to 1 inch, but our thickness is 3.25 inch. So we can't get exempted by the first item, but just assume it's okay. We want to review the other condition as well. The second condition says the hydrostatic testing is required. So sometimes you might perform the pneumatic testing in a certain condition. We're going to review this point later on when we are talking about the pressure testing. You have the hydrostatic testing and pneumatic testing, and it's not the optional to use the pneumatic testing. But in a certain condition, you can use the pneumatic testing instead of the hydrostatic testing. This says to you, you can use that opportunity over there. It's if you want you use the UG20F, you should forget about the pneumatic testing. It should be absolutely the hydrostatic testing. Also says the maximum design temperature shouldn't be warmer than 650 degrees Fahrenheit. As far as I remember, our design temperature was 700 degrees Fahrenheit. So we are also hit with this one. Nor colder than minus 20 degrees Fahrenheit. Our minimum design metal temperature is minus 30 degrees Fahrenheit. You can see we are hit with the condition number 1. We are being affected with the condition number 3. We can't use them by 1 and 3. But let's continue and see what's the other item included on the UG20F. The other one is the no thermal or a mechanical shock loading. So if you want to use the UG20F, your pressure vessel shouldn't be on some loading like a thermal loading or mechanical shock. You know, sometimes the compressor works and makes some surge on the pressure vessels and creates some vibration or some loading or thermal shock. Sometimes the temperatures go 700 degrees Fahrenheit, comes to the 100 degrees Fahrenheit, and some temperature fluctuation. So if your pressure vessel is going to be work in that condition, so you can't use the UG20F. So for our case, for our pressure vessel, we don't have those issues, but generally this is one of the conditions that you need to be considered when you want to use the UG20F. The last one is a no cyclic loading. Cyclic loading is a regular, in a time base, the fluctuation of the temperature or pressure. You know, it's in a minutes goes to the 600 degrees Fahrenheit and then comes to the 400 degrees Fahrenheit. It's a very regular, you know, loading that is considered in the design of the pressure vessel. So if your pressure vessel is going to work on that condition, also you can use the UG20F. But the one we affected by is the thickness, because our material SA516 grade 70 belongs to the curve number D, and the curve number D can be exempted up to 1 inch, but our thickness is 3.25 inch. So we have to move forward to see if we can get exempted by the UCS 66A. I put in a screen a curve, and this is a curve that you need to make an assessment. In the vertical axis on the left side, you can see it's the minimum design metal temperature, and the horizontal axis is the thickness. So, and there's a 4 curve. Curve A in the top, curve B in the below, curve C below of the curve B, and the curve D below the curve C. As you remember, I said that the curve D material, the material that assigned to the curve D material, are more tougher than the material assigned to the curve C, and the material assigned to the curve C are stronger than the material assigned to the curve B, and the curve B is stronger than, from the toughness point of view, to the curve A. Now, what we are going to do in here, we're going to draw 2 lines. My thickness is 3.25 inch. I'm going to draw a line from the 3.25 inch to cross the curve D, and then I'm gonna draw a line from minimum design metal temperature, which my condition in the design documents is minus 30 degrees Fahrenheit. I'm gonna draw a horizontal line, and they're gonna cross each other below the curve D. As you can see in the screen, they are crossing each other below the curve. So this indicates to me I have to perform impact testing. I'm not getting exempted, because if it would have located or placed on the curve, exactly on the curve D, or any point above the curve D, I would have been exempted. But now I'm falling on below the curve, not even on the curve. So below the curve. Below the curve, it means you are not getting exempted. But if you can see, there's a 2 point on the red line I drew on this curve. You can see in this screen, one of them is minus 30 degrees Fahrenheit, which is my minimum design metal temperature for this pressure vessel, and the other one is 14 degrees Fahrenheit, which exactly is on the curve. So this says to me, if my minimum design metal temperature would have been 14 degrees Fahrenheit instead of minus 30 degrees Fahrenheit, I would have been exempted right away, because you can use this material SA516 grade 70, which belongs to the curve D, to the 14 degree Fahrenheit with this thickness 3.25, with a thickness of 3.25 without any impact testing, and you could get exempted from the impact testing, but you can see we are below the curve. If you go to the left side of the curve, as you can see in the screen, you can see when the thickness reduced and the condition gets better. It means you can use the material on lower temperature. When the thickness goes high, so you actually having an issue. So since my temperature, my thickness here, my wall thickness is in here is 3.25 inch, my hands are tight in here, so I can't get exempted by the UCS 66A, and you can see in here that we are in the below the curve. By the way, the ASME code section 8 division 1 to make it convenient to use and avoid any drawing the line and crossing the curve, and might be some errors happens, then they are changed and converted that curve to a table, and they projected all the points which falls on the curve, and then created the curve that you can see in my right, and you can see there's a 4 curve columns or in the table or in the chart: curve A, curve B, and curve C, and curve D, and then the left hand there is a thickness value. So you can find out any materials assigned to the curve D, what is the minimum design metal temperature that you can use that material without any impact testing. Like the one in the screen, you can see for a thickness of 1.125 inch, you can use this material without any impact testing up to minus 26 degree Fahrenheit based on the chart. So this chart is not a new thing. This is the same curve. They just converted to the chart to be more convenient to be used. So if my pressure vessel would have been 1.125 inch, I would have been used this material without any impact testing up to minus 26 degree Fahrenheit. So let's go forward, and there's another screenshot from this table you can see in this screen, and you can see the thickness of 2.375 inch, and in the curve D you can see I can use this material up to 2 degree Fahrenheit without impact testing, but this is not going to work for me. My thickness is 3.25 inch and my minimum design metal temperature is minus 30 degree Fahrenheit. Now we are moving forward, and another screenshot from this chart indicates to you that for thickness of 3.25 I can use this material up to 14 degree Fahrenheit without impact testing. So 14 degree Fahrenheit, and I am in the minus 30 degree Fahrenheit that I can use this material. Now we have to go to the next step to see if we can get exempted by the UCS 66B, because we couldn't get exempted from the UG20F, we couldn't get exempted from the UCS 66A, and we couldn't get exempted from the UCS 66A. Now we are going to try to UCS 66B, which is a coincident ratio as a mix of the calculation and assessment. The coincident ratio is the curve that you can see in my right. We're gonna calculate a coincident ratio, a formula is there, and then we can see if we can get some reduction in our minimum design metal temperature. I mean those 14 degree Fahrenheit that you see in the chart, to see if we can get some bonuses from this chart and to get exempted from the impact testing. The point is, in here we never gonna ask you to calculate the coincident ratio. It's very design implication on the calculation of the coincident ratio. Coincident ratio always is going to be given to you, and then you're going to ask you to look at the temperature reduction or adjusted minimum design metal temperature. But just to know what's the concept of the coincident ratio I calculated, you can see my right, is that, you know, we designed this pressure vessel at 700 degrees Fahrenheit, and our allowable stress was 18,100 degrees Fahrenheit. But when we are talking about the brittle fracture and minimum design metal temperature, is for some condition that this pressure vessel is going to work at minus 30 degrees Fahrenheit, right? And at the minus 30 degrees Fahrenheit, our allowable stress is not 18,100. Our allowable stress is a 20,000 psi. So 18,100 psi was the allowable stress at the 700 degrees Fahrenheit, which we read that value from the ASME section 2 part D. But at the room temperature or minus 30 degrees Fahrenheit, our allowable stress is going to be 20,000 degrees Fahrenheit. And you remember from the design formula, they are in the opposite direction. When you consider the higher allowable stress, you're going to get a pressure vessel with the lower thickness. So we are going kind of get some credit for that. Another credit that you're going to get in here is that, you know, your actual thickness, the nominal thickness is 3.25 inch. But it wasn't a 3.25 inch our T minimum. We calculated something and then we added to the corrosion allowance, and because that value wasn't available in market, we got a material with the higher thickness. So we are going to get for a little that thickness that we because of the market availability, because that number came with the decimals and some digits, so you can get that plate with that thickness. You know, when you calculate something, you can get exactly the same things that you calculated. You have to get a higher thickness to match with what you calculated. So you are going to get a little bit credit for that as well. Another credit that you're going to get in here is that, you know, your design pressure is 900 psi at the 700 degrees Fahrenheit, but we're talking about here about the minus 30 degrees Fahrenheit, and it's like that when your when your temperature comes down, normally your pressure also decreases. So your temperature decreases, your pressure also is going to be decreases. And then might be at the minus 30 degrees Fahrenheit, your pressure is not 900 psi, it might be 600 psi. I made this assumption and I calculated the coincident ratio that you can see the formula on the left side of the curve, which is coincident ratio is equal to TR multiplied to the E joint efficiency and divided by TN nominal minus the corrosion allowance. And then, as you can see in the calculation in the right, I calculated the coincident, I calculated first required thickness, and then I calculated the coincident ratio. And you can see then the required thickness, I calculated the thickness for the 1.83 inches. As I mentioned before, nobody expects you to calculate this. 1.83, and here is our the calculation for the condition I told you, 600 psi instead of the 900 psi, 20,000 psi for allowable stress instead of the 18,100 psi. And then I got a thickness of 1.83. Now I'm going to calculate the coincident ratio, and 1.83 divided by 3.125. Where did I get the 3.125? I deducted the corrosion allowance from the nominal thickness. I put on the denominator, and the numerator is the value that we calculated for a TR. And then I get a coincident ratio of the 0.58. 0.58. As I said, you always is going to be given to you a coincident ratio. This process that I explained just to let you know what's the concept behind of the coincident ratio, and then you can comprehend that in an easier way. Nobody expects you to calculate the coincident ratio. You're going to get always the coincident ratio. I'm going to ask you to determine how much we are getting the bonus for that. Now let's see how much bonus we can get for these credits that I mentioned to you. Allowable stress, and then the higher thickness that we have in here, and then the lower pressure. You can see I look at the 0.58, I draw a horizontal line, it's crossed the curve at some point, and I draw a line from the cross point to cross the lower the horizontal axis, and it's going to cross that at the 42 degree Fahrenheit. So actually I'm getting 42 degree Fahrenheit bonuses for this. So what was our temperature that we could use this material with the 3.25 inch without impact testing was the 14 degree Fahrenheit. Now I'm going to deduct 42 degree Fahrenheit from the 14, just because I'm getting some credit in here, some bonuses in here. So my new temperature is going to be new MDMT without impact testing. Okay, you always have an MDMT, which depends on your user that's provided to you for designing a pressure vessel, or you are having another MDMT that you always talks about that. You know, my MDMT without impact testing is this. So it means this is the lower temperature that I can have without impact testing. And here is minus 28 degree Fahrenheit. It means this is a new adjusted value. Your previous value was 14 degree Fahrenheit. Now your adjusted value is minus 28 degree Fahrenheit because of those credits that I mentioned in here. It means I can use this pressure vessel without any impact testing up to minus 28 degree Fahrenheit without any impact testing. But this is not going to work for me because my MDMT is minus 30 degree Fahrenheit and this is minus 28 degree Fahrenheit, and I'm short by 2 degree Fahrenheit. So I just was some kind of an improvement in here. I came from the 14 degree Fahrenheit to the minus 28 degree Fahrenheit, very close, but actually I couldn't get exempted from UCS 66B, and I have to move forward to see if I can get exempted by the next item, which is a UCS 68C. What's the UCS 68C says? Says this is a bonus only can be given to the P number 1 material. Our material is a P number 1. So we might use this option UG68C. Says if you are not required to perform post-weld heat treatment and you voluntarily perform the post-weld heat treatment, I give you another 30 degree Fahrenheit bonus. It means your minus 28 degree Fahrenheit can be deducted to the minus 30 degree Fahrenheit and goes way, way, way below minus 30 degree Fahrenheit, which is a great, and then you can get exempted. But there's one issue in here. We are having a requirement for post-weld heat treatment for this certain pressure vessel. If you remember, our pressure vessel is lethal services, toxic material, and it was a code requirement to perform the post-weld heat treatment when your service is a lethal services. So we can't use this choice. Also, we are affected with the another things, with the thickness requirement. If you remember, we have to perform post-weld heat treatment when our thickness is over 1.25 inch. So our thickness is 3.25 inch. So for two reasons, we have to perform post-weld heat treatment. First, because of the service, and second, because of the thickness. So, but the code on the UCS 68C says if the PWHT is not requirement for you and you are doing these things by your own choice and voluntarily, but it is the voluntarily or by the choice, by my own option is not going to work in here because I am the compelled and forced to do the PWHT. So